we are going to cover how to implement the boundary conditions in finite element method. And I think it's one of the topics that should be particularly, I don't know if interesting, but particularly important for you. And let's, well, just please help me with that. We need, again, the 2D case. No, but this one is like, what should you get? You should get ux du dy, and this one means, because you need to end up with something that will be the matrix. So you cannot write this because it would only give you scalar value. Or sorry, no. That's good because we've got a scalar. No, but the problem is if you've got a vector equation, then you need to do something that is analog to that, and then it's a bit more tricky to write it really properly. Okay, so for this scalar case, it's fine. Plus okay, let me write this, the omega. Now, I'm not going to write the whole geometry transformation for the 2D case and the whole discretization, but you already know what to do with the gradients, how to replace u by simply the sum phi j, phi j at psi, eta, and so on and so on. Let me focus right now how to implement the boundary conditions. And let's start with the natural boundary conditions. And the natural boundary conditions for the finite element method are, you see this term is integrated over the boundary. So it's a natural way to implement the which boundary condition? This one. Well, especially if we start with, like something like that, then you should remember that really calculating something like that at the boundary means some flux at the boundary. And exactly the same naturally appears in the weak form. So it's a natural way to implement the boundary condition, the Neumann boundary condition. That's also why it's moved to the right-hand side of the equation, because if you know your Q, this means that you know this value, and it's a known value. So you can simply reintegrate over the boundary. You need to use, let's be a bit closer to the discretization. So you would choose some function v. What it means, if you want to implement the Neumann boundary condition, this is your mesh. Not a very beautiful one, but whatever. Now, first question, if you don't do anything and you skip this term, what does it mean?
That this flux is zero.
Exactly. So if you don't do anything, if you do nothing, you will end up with homogeneous Neumann boundary condition everywhere on the domain, on the boundary of the domain. Then, if you want to implement the Neumann boundary condition with some specific flux, what it means that for your discretized case, maybe I do not want to expand all these terms to show the full flavor of the discretized version, because it won't help you much to write this in the expanded form. But let's try to imagine at least part of it, so that you understand it not by waving hands. Let's assume we want to implement the Neumann boundary condition at this part of the boundary. Let's say this Q equals 5, and maybe everywhere else Q is equal to 0, okay? What should we do? We already know that the finite element test functions are global, but one of the test functions that generates, let's call this node 7th. The V7 is something that has got value of 1 here, and it drops here, and drops here to 0, right? So in particular, if you plot your V7 function along this edge, it's like, having a linear function from 1 to 0 at the boundary. So what it means, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11? Well, whatever. How many? 11? Okay. U11, U1 matrix. Let's assume you have already calculated all the entries here. We know how to do it: Gaussian integration, points, gradients, etc., and you come up with the values. Right now, let's see what to do on the right-hand side. For a moment, assume no source term, simply 0 everywhere. The only thing that we've got are boundary conditions. Then what do we need to do? The boundary conditions are the only things that go into the right-hand side vector in this simple case. So, assuming we've got V7 equal to 1, and we are assembling the equation for I equals 7, then we need to calculate over the boundary where we are imposing this boundary condition. So we know that here the boundary condition should be 5, 5, and 5. So we got, what do we need to compute? 5 times distribution of this function, of this test function, over that portion of boundary. And then something like that goes here. So let me write, well, whatever it should be. Let's call 5. You will understand from 7 to 5. Obviously, these are not values. But along this edge, you need to calculate integral along this edge. We have said, okay, our Q is maybe, okay, Q that you know, and Q is, for example, 5 times V7 in that case, d gamma. Okay? Looks good? Obviously, nothing comes from this element, because here we assume that Q is is 0. What comes next? Let's say this node is 3. So already here, when we need to assemble this one, then the shape function, the fifth one, is composed of this, gives contribution here. So we already, when assembling the fifth equation, so well, I equals 5, somewhere here, we need to integrate, well, from 7 to 5, what? V, where Q times V5 at psi, and it's one-dimensional. You need to calculate one-dimensional integrals then, only along the edges, plus, well, what? 3, 5. These are scalar integrals, so if you flip the order of integration, doesn't make difference. Q times V5 at psi, but in the other element already, times d gamma. Okay? Then we would need to do something like that for that node and for that node. So you would end up with contributions to 4 different equations from this forcing. That doesn't look from your faces that it's very clear for you. You can forget this and have a look at this integral. It's something that you need to understand how to implement. This product is something that you know. VI functions, these are the test functions, generate test functions in 2D, but they give some trace, some projection onto the boundary. And they are linear on the boundary. And you only need to take known value times the one-dimensional linear test function to calculate the integral using the Gaussian quadrature points, 1D Gaussian quadratures, along that portion of the boundary, well, and plug it into the, not really, yeah, like into equation, but on the right-hand side, because it's something that is explicitly known. Okay? So with the Neumann boundary conditions, it's pretty simple. If you've got 0 Neumann condition, well, you don't do anything. A physical remark, that was a nice example to show you how to implement Neumann boundary condition. For this steady state case, such a set of Neumann boundary conditions wouldn't work.
Yeah.
You know why?
Because this is without mass matrix, it will be like equivalent to pumping energy into system to the infinity.
Exactly. Imagine that you've got some portion of boundary and Neumann flux equal 5, and everywhere else Q equals 0. What does it mean? If you imagine that your diffusion problem is like energy equation and heat conduction, and you've got steady state, what does it mean? You're pumping in energy. You've got insulated walls. What's the correct steady state solution? No. Like no. So it's simply not a correct set of boundary conditions, but mathematically not a correct one. But I just wanted to explain you the implementation and numerics behind that, not the proper set of boundary conditions. Right now, let's move how to implement this for the Dirichlet. Boundary condition. And let me move back to the 1D example again. Just 3 elements. And let's assume we want to have u equals 0 here, u equals 0 here. What was the local matrix? Was it like 1 minus 1 minus 1, 1, I think? Well, divided by delta x. Yeah. So you can quickly assemble that without doing the mixed order. This would be 1. I believe minus 1 minus 1, 1. Then again 1, which is already 2. Minus 1 minus 1. For SU, yeah, what else? Minus 1. 2 minus 1.
I believe that's...
This is 1 minus 1 minus 1.
Yeah, I think this is the end of the matrix because you got like 4 points and here is 1. Yeah, exactly. That's correct.
And you can see in the simple case.
And you missed minus 1 in the lower right corner. Yeah, here exactly.
Okay, that's good. Now let's focus. We've got 3 elements, 4 nodes, and without remembering anything about the boundary conditions, that would be the matrix that we would come up with when assembling the global matrix of the system, right? But if we are interested in calculating the boundary value problem with Dirichlet boundary conditions, this already means we don't need to have an equation for that value because we know it. And we don't need to have the equation for this value because we also know it. So we are only interested in calculating 2 values. So what does it mean? It means that u1, u2, u3, u4 equals sum f1, f2, f3, f4. Now, this means that, well, we don't need to have the equation for u1, so we delete it, because we know u1 is simply 0. Then the problem is that equation 2 needs u1, right? Well, but it's 0. So if we omit it, we didn't change anything, right? So what we can do is we can simply delete the column. Let's see u4. We've got the equation for that, but we don't need to have the equation because we know what it should be. It should satisfy the boundary conditions. So we delete the equation. And same procedure. Well, equation 3 needs u4, but it's 0. So let's delete it. And the final system that we come up with is that it's reduced. It only involves all internal nodes in the mesh, not the Dirichlet boundary nodes. Okay? It's the way how actually everywhere I have seen is explained how Dirichlet boundary conditions are implemented or derived for the finite element method. It's the classical way of showing that, I would say. However, it's not convenient at all for implementation because what it means in 1D case, okay, you can do it. In 2D, 3D on unstructured meshes, it means you've got a large matrix, then you want to delete some boundary nodes. Just a minute, okay? You want to delete some boundary nodes, then it means that they are not ordered properly, they are not numbered properly. So you probably need to renumerate your mesh. Then when you end up with the result, then you need to renumerate it somehow.
You just have to like store
the maps.
Yeah,
Yes, you can.
transformation matrix.
Yes, you can. But it's not very convenient. You need to delete something from matrix. You're building a smaller matrix. You've got some overhead to do it. In the 2D or 3D case, you don't gain so much because, well, what do you gain? Maybe you've got a couple of million unknowns in a 3D mesh. How many nodes have you got on the boundary? 50,000 compared to 5 million.
Well, it depends on the case because
yeah, I know.
If we are talking about like basically cube, all right, it's not much. But if you are talking about radiator inside the cube, then the surface area is much more, and if you would like to impose the Dirichlet boundary condition on the surface.
Like you can do both. I'm showing this because it's really how finite elements are taught everywhere. And it's the classical way of doing that, but it's not the only way. Tim, you had some question.
Here we can delete the entire row and column, but it's just because u equals to 0. If it was constant equals to 1, for example, it wouldn't.
Yes, that's right. We will come to that in a minute. That's right. Just also see, or maybe let's answer your question first. We will be good with time. No, don't worry.
So.
Don't worry. What's the classical way of explaining the Dirichlet boundary conditions, but not the homogeneous zero Dirichlet boundary conditions, but having some value u equals to w, whatever it is? The classical way of explaining that is, okay, we are interested in finding the solution u with proper boundary conditions. Let's split it into ud, and ud is something that fulfills the Dirichlet boundary conditions and is arbitrary everywhere inside, but it's correct on the. You can imagine that here, and the problem will be physically good. We want to say, okay, u equals 7. Then let's split the 2D solution into some 2D function that will be arbitrary everywhere inside, but it will have correct values at the boundary. Okay? Good? Plus u, maybe lower index, lowercase index, plus u0. And u0 means the solution of the original problem with the 0 Dirichlet boundary condition. So you split the solution into something that fulfills the Dirichlet boundary condition and something that has got 0 boundary condition. This function you simply assume and you know it. This function you need to solve. I mean, for this function you need to solve. Well, so what happens in the matrix notation and in the discretization? Well, if we make an analog to that, but let me but let me reorder the nodes a bit in a way that, let's say, we've got some A matrix, B, C, and D. And what's here? Here is UI, like internal nodes, and we have ordered the nodes in such a way that all the Dirichlet nodes are at the end of the solution vector. Okay. So how this procedure translates to that? Well, basically, we have deleted all the columns and rows responsible for acting on UD. Yeah, so what we've finished with was simply A times U internal and nothing else. So what do you do in the classical sense? Well, in the classical sense, you are also eliminating the rows and columns, but this way, that you need to apply A times U0, because of this one, in the discretized version, we only possess the internal nodes, and you know that by having only representation of the internal nodes, it will automatically satisfy the zero Dirichlet boundary condition. But then you've got plus B times UD equals your original F. Because you know that, and because you have assembled the full rank matrix, what you do in the classical formulation is that. So again, you've got a slightly smaller system of equations for the unknown values at the internal nodes. Your original portion of the, because you've got some Fi and Fd, so your original portion of the right-hand side vector minus rectangular matrix times Dirichlet values at the boundary. You don't need to solve that, because what's that? This would be like obvious equations for the values at certain nodes. Good? Questions? Because we've got 2 minutes, and I promised you that we will be in just 1 minute already.
And is it in our toolbox that we have like still full matrix?
Yes.
We've got
with diagonal with ones and
Exactly. We do it differently in the toolbox. For this, I would say, the other choice is not eliminating the rows and columns and renumbering all the things, but you can keep them with the original values, like 1 here, minus 1, everything that you had. What we are doing is we are always working on the full matrix, but we are saying, okay, we don't need to have the original equation for U1, but we need to enforce that U1 is 0. So let's erase all the entries in that row. Let's write 1, and let's replace this by 0, because it's already the proper equation to enforce this boundary condition. Then if we do that, let's also replace the whole row by just 1 on the main diagonal, and replace that by 0 in a minute. And now you could have doubts what happened to the other equations, but once you've got your proper solution to these equations, then you see, okay, you've got the second equation that actually acts on U1, but if you've got already the correct equation after converging the linear solver, then U1 is 0, so it does not interact in any way, and as it wouldn't interact in the procedure with eliminating the columns. Now, the nice thing about that is you don't need to do this splitting to implement Dirichlet boundary conditions, because, well, you want to have 5, no problem.
Basically, the code is more readable and more manageable
On the side of user who's explicitly doing
And isn't there a problem that because of such change in the matrix, we lose the symmetry C?
Yes and no. That's a
Like,
good.
I know, like with backslash, it's not a problem,
But if you would like to use PCG or something like that.
So yes and no. We lose symmetry and we do not lose symmetry.
like I know if we would like add the operation of taking it to the right hand side, like we have still the symmetries.
It's a really good question and difficult to answer quickly, but you can come up with 2 explanations. One explanation is, okay, you still have got the matrix that represents diffusion or a problem that is symmetric. So, well, you've modified something, you've got still the phenomenon which should be symmetric. Why should it behave differently? But from the other side, you look at the matrix and, well, it was symmetric and it's not anymore. And it turns out that if you even follow, like step by step, I have done it during my PhD with Professor Szumbalski, because we couldn't understand why this works and works correctly, even if you run PCG, like conjugate gradient, or any Krylov solver. It turns out that if you do it this way, and you go step by step with every matrix vector multiplication in the algorithm of the Krylov subspace solvers, it turns out that like as these portions of the vector that you have enforced to be 0, whatever else, they end up being like 0 automatically. So although you don't have symmetry in the matrix, then because of you require this, well, to be 0, whatever you want to have, it looks like all the operations go the same way as the matrix were symmetric. But you need to go to through the algorithm.
Like now I understand, because like in the PCG you base on the multiplying matrix with a vector, so and since those values for the Dirichlet boundary doesn't change,
so it works. It's so to say invisible for the Krylov subspace solvers. Questions about implementation of boundary conditions?
Why don't we change directly the values of U1 and U4? Create like a new step on each iteration. We do a new step, assigning U1 equals U4 equals 0.
But how would you do it?
At the beginning of each iteration.
But basically, it's a linear system. It's a linear system of equations with a matrix of given coefficients, and you need to input a matrix and the right-hand side to the linear solver. And that's what you can do, and then you get the result.
But why would, if we specify some, okay, yeah.
I think if you like wouldn't change the matrix, it would be like the determinant would be 0, or I'm not sure.
Yeah, okay, it's a different problem.
Yeah, conditions, but yeah.
but you need to define such a linear system that whose solution fulfills your boundary condition. Okay, let's continue with what we finished recently. Recently, it was a long time already, but I think what we came up with is the discretization of the find element method. What we did was we have covered everything for 1D with the implementation of the Dirichlet boundary conditions, where you might remember that we usually in find element method define the essential conditions are zero Dirichlet boundary conditions. If you want to impose any non-zero Dirichlet boundary condition, you basically split the solution into a known field that is arbitrary but fulfills the Dirichlet boundary conditions, and unknown field everywhere within the domain. Then we have also studied two ways to technically implement these boundary conditions, that you can really split the terms and eliminate some rows and some columns from the matrix, but we can also do it the other way around. We can basically enter once on the main diagonal respective values in the right-hand side vector and proceed this way. And we also have stated that basically these matrices are no longer symmetric, at least very literally speaking. But it turns out that all the methods like conjugate gradient work correctly for these matrices too, because so to say the operations that the conjugate gradient is making make this slight non-symmetry of the matrix, so to say, invisible for the conjugate gradient methods. That's why it works. Any questions or things that you think need to be reminded? We have also covered the geometrical transformation and why we need that. Good. So let's proceed. Let's proceed to the third type of boundary conditions. And let me remind you the weak form of the scalar passive transport equation that we've maybe not finished, but that we had recently. The diffusion matrix equals the right-hand side vector plus the Neumann boundary. Here we've got also the diffusivity, unit normal vector times gradient of phi times v and the integrand. Good. So what we were discussing recently is the case where we do have some portion of the Dirichlet boundary condition, some portion of the Dirichlet boundary, and some portion of the Neumann boundary. Right now, I'm interested in showing you what kind of impact on the discretized form and the matrix structure has got the implementation of third type boundary conditions. So let's remind, the third type boundary condition is or at the boundary, let's call it R, like Robin. So we need to have equals, like, for example, it's C times the solution, plus minus whatever, however you define that, some given value. You can write them differently, but the idea is that you need to have some coefficient multiplying your solution value times some constant value. Okay, what happens then? Let's see, the natural way to implement such a boundary condition is this term is present exactly here. So what you basically do is you take this integral and we need to write, okay, this would be minus. Here we've got, it's the same. We need to enter this formula. It's Cu minus U infinity times the test function at the boundary and integrated over the boundary, the Robin boundary. Okay? Can you imagine that? Like, the trick is that here, everywhere, we are dealing with surface integrals, well, domain integrals. Here we are dealing with the boundary integral. So you need to remember that if you've got some elements lying here on the boundary, they do have their two-dimensional shape and test functions, but you're calculating this integral over the boundary, which means that you need to deal with one-dimensional projection of the two-dimensional function on onto the boundary. So you end up with normal one-dimensional shape and test functions of the finite element method. But let's have a look here. This one can be splitted into minus Cu times V plus gamma Robin Cu infinity V d gamma. And let's analyze that quickly. That's the constant value that we know from the boundary condition. That's a known coefficient. So we need to multiply it by the one-dimensional test functions. And where will it go once we calculate it? In the discretized system of equations, where will it go?
To the right-hand side.
Exactly. It will go to the right-hand side because here everything is known. Times the discretized version would be, we've got some VI function, and it would go to the ith row of the right-hand side vector. Where will it go?
Yeah.
Exactly. This will go to the matrix because this one is obviously J like shape function. I don't remember what kind of notations we've been using. Let's say shape function J times coefficient U J. So U J's will be the unknown coefficients. This will go directly to the matrix. And just have a look that this one forms something that is very, very similar to a mass matrix. Actually, we've been discussing so much of the diffusion effects that I didn't talk much about the mass matrix. The mass matrix would come out, for example, from the discretization of the time derivative. Why? Because it's like having the function u times v. This is the term that we would integrate. Obviously, if you've got such an expansion for u, the shape functions do not depend on time, so the time derivative goes out, and the only thing that you're left are the shape functions times the test functions. So how does the mass matrix look like? It looks like for a given element, this would be like having phi I, phi j, where in the element, integrated over the element. Okay, good. So what I want to underline here is that implementation of the Robin boundary condition implies that you have some additional contribution to the right-hand side vector, as in the Neumann boundary condition, and you will have like mass matrix-like contribution to the matrix of the system. And this is the part where imagine you could have just the Neumann boundary, and we remember that assembling such a system with the diffusion matrix with just Neumann boundary conditions leads to the effect that the diffusion matrix is singular, because you can choose any temperature level for a linear problem. You can choose any temperature level where you will have where the solution will be okay, right? Because for the heat transfer only the gradients matter and nothing else. Like if you've got Neumann boundaries, you haven't got a prescribed temperature level at which the temperature solution should be located. You only have got this if you define the Dirichlet boundary condition. But so speaking numerically about the properties of the matrix, it means that you would have a singular matrix D, but once you apply a Robin boundary condition, you do have some additional contribution to the matrix, and this contribution is like mass matrix-like, and the mass matrix is not singular even without any boundary conditions. So once you do this contribution, then your final matrix, something like, well, not really the mass matrix, but something that is similar to that, is already well determined. I mean, it's not singular, and you've got just unique solution to such a linear problem.